Yeah, so there's a voltage difference between inside and outside. Inside is typically around minus 70 millivolts. It can vary anywhere between minus 90 and minus 50 or 60 millivolts. And with respect to outside, where you take the outside as a ground potential. And so neurons, the cables of the neurons, like the dendrites or the axons, are capable of propagating these signals, these electrical signals. This is just an example. This picture illustrates how it works. It's just like an electrical wave, right, propagating down a electrical cable. The only difference is when you look at electrical engineering, the electrical cables, the current there is electronic current, whereas in neuron the currents are ionic currents. It's not carried by electrons; it's carried by various ions, particularly sodium and potassium. Okay, so the nature of this wave propagation also is varies depending upon which part of neuron you're talking about. Typically, again, there are no absolute rules in biology. There are always exceptions. But on a dendrite, the propagation is lossy. That means as the wave propagates, the amplitude of the wave keeps shrinking and the wave keeps spreading in time. Whereas propagation on axons is non-lossy. So this is an example of wave propagation in dendrite. So you have initially you have the sharp wave, as you can see here, and with time that sharp wave spreads in time and also loses amplitude, becomes shorter and shorter. Now with the soma, things are different. There's something special happens. A special kind of electrical signal or a voltage signal is generated in the soma, particularly in this part of the soma called the axon hillock. Right. So what happens is when you inject current into it, I think of the neuron as some kind of a simple spherical shell, and if I inject current into it, I of t, right? Inside there is a voltage. I'll call this V of t or Vm of t to indicate membrane voltage. So in response to the current, there will be a response in voltage. So if I give a current impulse as input, so this is my A of t. In response to that, Vm also increases, right? Let's say something like that. I mean, just a hypothetical change in the voltage. So that change varies with your increasing current amplitude. So when I give, so here, let's say applied current is like this, just a pulse, right? And this is so many, let's say, picoamperes or something like that. Okay, micro. In response to that, the voltage also increases and falls back. So actually, since so we'll see that later, but the membrane of the neuron is like a series of radius of resistance and capacitances. So it's like an RC circuit as a basic approximation. So when you give an input current, which is like a pulse, in response to that, the voltage increases exponentially and also falls exponentially. It looks something like this. So this is the input current pulse. This is the voltage response to that current pulse. Anyway, it's like you can think of this picture as an approximation. Input is a rectangular pulse, output is also the voltage response is also rectangular pulse. So it will come back to the baseline value of minus 70. Now, as you keep increasing this current amplitude, the voltage response also keeps on increasing. But this monotonic increase goes only up to a point. Beyond a point, when you increase the current amplitude, there is a sudden sharp increase in voltage, right? It's a nonlinear increase in voltage, where the voltage, which is normally negative, goes all the way, crosses zero, and becomes positive, goes to a peak value, and then quickly drops back to the baseline value of minus 70, and actually goes even below that, right, to even more negative values like minus 80 or something. Then slowly comes back to the baseline value of minus 70. This sharp voltage spike is very peculiar about a neuron. The other cells in the body which also have electrical activity, but they don't always produce this kind of a sharp voltage spike. And this kind of a spike is called an action potential. Okay, this is a nonlinear response because up to this point there's a linear increase to the input current, but beyond that, there suddenly is like as if some threshold is crossed, the sudden increase in voltage. And wave also propagates on an axon. The wave propagates on the axon is quite interesting. So this is the axon, and axon has this myelin sheath. At least there are special axons which are endowed with a myelin sheath, a myelin coating. In these cases, and axons in general have special molecular machinery by which they are able to charge the signal as it is propagating down the axon. So normally in a passive cable, we have a propagating wave. So it's a passive cable. If you have a propagating wave, it loses energy and right like in a dendrite as it propagates. Whereas in case of an active cable, right like an axon, as it propagates, it doesn't lose energy. Whatever is the shape initially it has, it keeps that shape. Keeps that shape intact. So that's what you see in this picture. So there is no loss of amplitude, no spreading in time. So this kind of a propagation of wave on the axon is something special to the axon. So this wave that is shown here is action potential. This is a simple animation of how the action potential propagates down an axon. Right, whereas this propagation will be very different on the dendritic side, as we have seen before. So we said there are 4 components of neural signaling. There is signal propagation on the dendrite, then this kind of a special generation of action potential in the soma. Then there is propagation of the signal along the axon. Then finally we come to this 4th component, which is called neurotransmission. So which is the most important part of neural signaling, because so this is where one neuron right makes contact with another neuron and sends its signal. So this is axon of one neuron, right, and this is action potential. So that propagates down the axon. Once it reaches the synapse or the presynaptic terminal of first axon, this electrical signal gets converted into a chemical signal. So there is a release of a chemical by the presynaptic terminal, which acts on the postsynaptic terminal, and the action of the chemical on the postsynaptic terminal generates a new electrical signal on the postsynaptic side, which then propagates along the cable on the postsynaptic side, and this cable happens to be a dendrite, and this cable happens to be an axon. So this signal happens to be an action potential. This signal has a different name. I'll come to that later. So basically, at a synapse, one electrical signal is converted into another electrical signal. In between, it is mediated by a chemical signal, right, by the release of a chemical by the presynaptic side. Okay, so this simple schematic, this kind of the schematic shows this as synapse. So this is a button, which is the presynaptic terminal. So synapse has 2 sides: the presynaptic terminal, which is on the axonal side of a neuron, and the postsynaptic terminal, which is the dendritic side of another neuron. So when the action potential comes to the presynaptic terminal, so the chemical is released, and because of the action of this on the postsynaptic terminal, a voltage is produced on the postsynaptic terminal. Only thing is, the voltage produced on the postsynaptic terminal has a very different shape compared to the voltage signal on the presynaptic terminal. On the presynaptic side, since it's an axon, it's always in the form of action potentials, which has a standard shape and size. And typically, this I forgot to mention that this action potential, whenever it is produced, it always has a standard shape and size. That means this amplitude is kind of almost fixed. Sorry, roughly about 100 millivolts, because it goes to about plus 30, right, on the positive side. And the duration of the signal in time is about 1 millisecond. Okay, and so it varies, but 1 millisecond is a typical figure in animal and nervous systems or neurons. So that is how it is on the presynaptic side, and because of that property of the action potential, this kind of a response is called an all or none response. That is, it responds fully or doesn't respond at all. So it's a kind of exaggeration. It's not all or none, but it's all or very small. It's not none exactly, but anyway, that's the spirit of it. That is, it's a you can think of it as some kind of an atomic response. That is, When it responds with a standard shape and size, signal with a standard shape and size. So it's called an all-or-none response. Whereas on the post-synaptic side, it is not like that. It is not so clear-cut. It is more graded. It is not yes or no. It's not so black and white. It's more graded. And this potential that you get on the post-synaptic side has the obvious name of post-synaptic potential, or PSP. So it is written here. Right? These are called post-synaptic potentials, or PSPs. So the action potentials, like I said, always has a standard shape and size. That is from the baseline value of -70, it's always positive. It is positive, has a fixed amplitude and duration. Whereas the PSPs on the postsynaptic side, they have a variable height. This amplitude is variable, it's graded, right? And it could be positive or negative. In this picture, I'm showing a positive voltage, but it could be positive or negative. And the height also could vary. So that is what is special about the PSP. So depending upon the nature of the PSP, whether it is positive or negative, the synapses have different names. Okay, and the signal itself has different names. If the PSP is positive, then you call it an excitatory postsynaptic potential. Okay, so that means the synaptic cell, postsynaptic cell temporarily depolarizes. So depolarize means, depolarization means VM is greater than 0 because the normal polarity of VM is negative. It's negative. So it is. So when the action potential is generated, the membrane gets depolarized. That means the voltage becomes positive. Then there is also something called hyperpolarization. Hyperpolarization. What that means is VM is even less than -70 millivolts. So normal polarity is negative, but the membrane voltage, the exact value is about -70 millivolts. In hyperpolarization, it goes even below that. It's more polar than normal. So therefore, it is less than even -70. So when you talk about, so all deviations are described by taking this -70 as the reference, right? So greater than that, if a voltage is taken to values greater than -70, it is, you said the input is positive, or there is a positive deviation. There is excitatory postsynaptic potential. If the deviation is less than -70, then it's inhibitory. So all the when it's excitatory and inhibitory, we are taking this baseline value or whatever it is, let's say -70 as a reference and describe with respect to that. So positive deviation is referred to as excitatory postsynaptic potential, negative deviation is referred to as inhibitory postsynaptic potential. So these are kinds of two kinds of signals on the postsynaptic side. If you have a positive deviation, you call it an epsp, and if you have a negative deviation, it's called an ipsp. So like I said, these signals, the PSPs are graded signals, unlike the action potentials. They can be positive or negative, and they can also be high or low. So it can vary continuously, it can take any value continuously from 0 to some maximum value. So in this picture, the EPSP is high, here EPSP is low, again here IPSP here is low, and IPSP here is high. Okay, so this is possible. This is something that you don't see in the action potential. So depending upon what kind of EPSP is produced, because on the presynaptic side, the signal is always of the same kind. It's a positive, the standard action potential. But on the postsynaptic side, signal can vary. It can be an EPSP or an APSP. So where is the difference coming from? So obviously, the difference is coming from the synapse, something about the nature of the synapse. So based on the kind of response that the synapse gives, they are classified differently. So if the synapse gives EPSPs, we call it an excitatory synapse. Or if a synapse gives an IPSP, it's called an inhibitory synapse. It vaguely put, it depends upon the chemistry of the synapse, and we'll see what the chemistry is in a minute. So to summarize, I said, there are 4 different components of neural signaling. You can think of neuron itself as some kind of a black box, right, with an input and an output. and inputs are the dendrites coming from other neurons, and you have all these signals, right, coming in from other neurons. And these are, mind you, these are PSPs, and all these go to a neuron and they all get added up, and we'll see all that later. And the neurons sometimes, right, so you see that there's this all or none response which is generated in the neuron cell body, right? So let us say that condition is satisfied, the neuron succeeds in generating an action potential. That action potential is generated from the cell and it propagates down the axon, goes along the axonal collaterals, reaches the synapse. At the synapse, it makes contact with some other neuron, the dendrite of some other neuron, and the chemical is released, and there is neurotransmission. So this chemical transmission of signal is called neurotransmission. So these are the four components. Also note that among these four components, the first three components are electrical signals. The genetic processing is an electrical process. The summation of the signal in a neuron and generation of action potential is all electrical process. Signal propagation along axon is also an electrical process. But the fourth step, where a signal goes from one neuron to another, it is a chemical step because it involves release of a chemical, and this is called neurotransmission. Now let us also look at this summation business, how exactly the summation takes place. So here is a neuron. Okay, the neurons are color coded just for sake of convenience, but otherwise neurons don't come in colors, obviously. Right. So this is take this yellow neuron, and it gets two inputs, one from this red neuron, another from this blue neuron. It turns out that the synapse between this red neuron and the yellow neuron is a positive synapse. This is an excitatory synapse. Similarly, the synapse from blue neuron to the yellow neuron is an inhibitory synapse. So now this graph here on the right shows what will be the voltage if you recorded from these neurons. So if you're recording from the red neuron, you'll see an action potential. And that action potential, when it actually crosses this synapse and reaches the yellow neuron, it will produce a voltage on the yellow neuron, which is shown as a yellow graph, right, in this graph, this plot. And since this synapse is an excitatory synapse, the response here is positive, so you record an epsp right, somewhere around this point if you put an electrode here and measure it. But on the other hand, if you look at the action potential generated by the blue neuron, which is given by this blue curve, the blue action potential, that propagates right down this neuron, and if it reaches the synapse, on the postsynaptic side, it generates a response, a PSP, and that happens to be an ipsp because here it is a negative synapse, an inhibitory synapse. So therefore, on the postsynaptic side, the deviation that you get, this yellow graph here, will be a negative graph, whereas this is a positive. So you see what is happening here is, one neuron is trying to inject some current right into this neuron, that is a positive current, thereby increasing the neuron's voltage. Another neuron is trying to decrease the voltage of this neuron by injecting negative current. So the thing is like this: if different neurons, give and inject different levels of current, both in terms of sign and magnitude, all these currents produce certain changes in voltage of this target neuron, the yellow neuron. Right? If the net effect of all these currents is such that the target neuron voltage goes beyond some threshold value, then the neuron gets into what is called an excited state, and it produces action potential, which then propagate right down the axon of this neuron. So this summation of all the signals coming to a neuron from other neurons, that is called spatial summation. Okay, because these are added up in space. There's a different kind of summation that also takes place. That's called temporal summation, which is shown in this picture. So here is an axon of one neuron, right, and a bunch of action potentials are coming. So from on the same axon, you are seeing a train of action potentials coming one after another, and all these fellows produce a PSP on the postsynaptic side. Assume this is an excitatory neuron, excitatory synapse, so it's positive. So in the first one hits the dendrite here, it will produce a PSP which is positive. It goes like this, and it starts falling. But before it starts falling completely, before it comes completely to the baseline of, let's say, minus 65, the second action potential hits. So therefore, it starts increasing further. And before that completely falls to the baseline, the third action potential hits, and then it goes up further. So you see that because of this action potentials coming in a quick succession, the voltage response on the postsynaptic side, right, involves an addition of the PSPs, and this kind of an addition or summation is happening in time. So this is called summation through time, or temporal summation. The first one is called spatial summation, like I just explained. Right, here is a neuron, it gets inputs from many other neurons. It so happens that this is a positive excitatory synapse, and this is an excitatory synapse. These are excitatory synapse, but there's no connection. Okay, there's also another inhibitory synapse, no connection, inhibitory synapse, no connection. So this neuron is getting excitatory connections, inputs from two neurons. Both of them tend to increase the voltage of this neuron. And if you if that increase is sufficiently high so that a threshold is breached, then this neuron gets excited and it releases an action potential, which then propagates down the axon. But consider this situation where it has two excitatory inputs and two inhibitory inputs here and here, right? And all of them just cancel off each other. So net effect, there is no change. Therefore, the voltage of this neuron hasn't breached the threshold, so there is no response. It won't produce any action potentials. So basically, a cell has to combine all its inputs, both excitatory and inhibitory. And if the net effect of that combination is still a sufficiently positive value, then the neuron gets excited. The threshold is crossed, and that is when this sudden signal is generated. So this is in summary, right? What happens, right? If a neuron gets inputs from many other neurons, if the positive inputs, if the negative inputs dominate, like in this case, right, the voltage doesn't cross threshold. The net effect of all the input is less than the threshold, so no action potentials. If the net effect of all these guys is greater than a threshold, then the neuron gets excited and produces action potentials. So this is a summary description of how a neuron works. And so like that, then the output of this neuron the signals go to other neurons and again influence other neurons in the same way, and so on and so forth. Now I like to compare this process, to take a human analogy. I like to compare this process to the way people have group discussions. So for example, when you go for campus interviews, you go for group discussions, right? So usually you are given some topic and let us say you want to argue whether the result of that question is yes or no. The answer to the question is yes or no. So usually the way it proceeds is somebody has an opinion on that, and then somebody explains why he or she has an opinion, and then gives opinion, is it yes or no? So that opinion is heard by other people, right? And the other people will receive opinions like that from a lot of other people. And if there are a lot of people saying yes, then you also revise your opinion, even if you're thinking no, right? And then you announce your own yes, which is heard by other people, and they keep on revising their opinion. So this is how the neurons are also working in some sense. So here again, if you want to capture the idea of inhibitory synapse or excitatory synapse, you can imagine that when people argue, when people discuss, they might have certain inherent biases towards each other, right? Suppose you think very highly of somebody's knowledge and intelligence. That person says something, something is true. You tend to believe that person, so you take that person's opinion with a positive weightage. So which means it is as though you have an excitatory synapse with that person. On the other hand, so you don't think much of somebody's intelligence. If the person says something, you don't believe that it is true. So it is as though that person has an inhibitory synapse to you. So when people like that debate with all these inhibitory, excitatory influences or biases, right? So that process is quite analogous to how neurons talk to each other in the brain. Okay, so that is a very simple summary of how signaling proceeds in the brain. Now I'll go into the same topic, but at a slightly deeper level, going into more details, and let us see how it looks. So until now, we just discussed neural signaling at a high level, describing the effects, but we did not talk about how the signals are generated. What is the molecular basis, molecular and cellular basis inside the neuron that generates all these signals? So we'll now in this section, we'll talk about the molecular basis of neural signaling. Specifically, we'll start with something really basic. How is a membrane potential generated? Because we said there is a membrane potential. There is a potential inside the neuron with respect to outside the neuron, which is negative. How is it even generated? Then normally we said it is about minus 70 millivolts. But when the neuron is excited, why does this value go to a high positive value and why does it rapidly come back to the baseline value? What happens? What's the basis of that? Similarly, how does the signal propagate along the axon? Why? How come it doesn't get doesn't lose amplitude? It doesn't get deteriorated. Then the last thing, what is neurotransmission and how is that chemical released by the presynaptic terminal? So let's talk about this. Now, like I said, when a neuron is in the resting state, there's a voltage of minus 70 millivolts. When neuron is in what is called excited state, this voltage undergoes sharp fluctuations in the form of action potential. So we already know this. Now, how does it happen? What is the base of this electricity? So neuron, the cell body of the neuron, right, is always bathed in an ionic medium, in an electrolytic medium, and this medium has lots of different kinds of ions. So, for example, sodium, potassium, chloride, and calcium. These are four major players that are involved in neural electrical activity. And like I said, neuron has two compartments. We talked about four major compartments in the brain, but in this context, two are relevant to us. The two compartments are extracellular space, or ECS, and intracellular space, SCS. So these ions are present both outside and inside, both intracellular space and extracellular space. Okay, so this interstitial fluid is ECS, and this is inside the cell where there is cytoplasm and all. Now, what separates these two compartments is the membrane, the cell membrane, which is also called the plasma membrane, which is made up of two layers of lipid molecules. Therefore, it is called a lipid bilayer, right? A lipid bilayer, a very explicit kind of an arrangement that effectively insulates the internal contents of the cell from the extracellular medium. So now different ions are distributed differently about this membrane. So for example, if you look at sodium concentration, sodium ion concentration is high on the outside of the cell of the neuron compared to the inside. So higher sodium outside, lower sodium inside. Whereas for potassium, it is opposite. Potassium is higher inside and lower outside. So roughly the values of the concentration are given here. Okay, and now there's a special molecules, and those of you who are in biotech would have learned all this stuff in some cell biology course or molecular biology course. But for others, I would imagine that these things are somewhat new, right? So there are these special molecules which are actually proteins, which form some kind of a pore, right, through which ions can flow and flow between inside and outside of the cell, right? These kinds of molecules are called ion channels, right? And these are the channels which allow passage of sodium potassium. Okay, and so these ion channels are selectively permeable. So they allow passage of sodium, potassium, calcium, and all that. But there are special channels to specific ions. So, for example, I'm making it quite simplistic. But anyway, let us stick with the simple story for now. We can look at more sophisticated versions of it later. So, for example, if there are potassium channels, these channels will only allow potassium ions. Okay, and if there are sodium channels, they only allow sodium ions. Similarly for calcium, right? Now, and these are so therefore they are selectively permeable. They allow permeation of only one ions. Then another property of these ion channels is they are not like a fixed hole in the membrane. This hole is dynamic. It can be varied. It keeps changing. So like it's more than a hole. You should call it like it's like a gateway. So this gate can open or close, right? If it is closed, it will block ions from flowing. Like in this case, it's closed, right? If it is open, it will allow passage of ions. It's when it is open. And this opening and closing dynamics of an ion channel can be controlled by many different influences, many different factors. So, for example, there is something called, and this opening and closing, this control of the open-close states of an ion channel is called gating. Because this ion channel acts like a gate, right? Controlling the gate is called gating. Now, this gating can be controlled, for example, by varying the membrane voltage itself. Okay, so if I control the voltage of the membrane, so for example, if the normal voltage is minus 70, if I inject current into it, positive ions into it, the voltage will go up, obviously. Right? Because you can think of neuron as some kind of a spherical capacitor. If I inject charge into it, the voltage of the plates goes up. So when the voltage goes up, right, certain ions actually open. It's a property of those ions. Right? It's a long story exactly how the voltage changes ions, the ion channels open close states. But we'll just stick with this simple story for now. For certain ion channels, when you increase the membrane voltage of that cell, the channels open. And such channels are called voltage gated channels. And not all channels have this property. Only some channels have this property, and such channels are meant to be called voltage gated channels. And and that kind of a gating process is called voltage gating. Okay, so in this case, you see that how when you change the voltage of a given channel, it become open. Initially, it was closed, and on the left side, on the right side, you see it's open. The other very important kind of mechanism by which you can open the channel is by using a chemical. The previous one is by using an electric signal, that is by varying the voltage of the membrane. The second one, which is also quite important, is by varying the chemical levels of some molecule. So that is called ligand gating because sometimes these ion channels have a small part of it that acts like a receptor. So we talked about the receptor concept right in the very first class, I think, first or second classes. When we talk about history of neuroscience. So this idea that chemicals can have action on neurons, right? So this action of chemicals on the neurons is through this mediation of something called a receptor. Receptor is, in case of an ion channel, receptor is simply a part of the ion channel itself. So the molecule which comes and acts on an ion channel, it actually binds with a certain part of the ion channel, which is called a receptor. So you can call it a receptor site, a location on the ion channel which acts like a receptor. So this is the chemical which is coming in to bind with the ion channel. It kind of sits in the slot, which is the receptor. Once it sits in the slot, it is as though the incoming chemical binds with the ion channel. When the binding event takes place, the channel opens. Here the molecule is bound, right? And then it allows passage of ions. So one of the ways in which, or one of the contexts in which this binding occurs in case of neural signaling is during neurotransmission. So when a neuron releases a chemical, right? It is this kind of a chemical that it releases. This chemical goes to the postsynaptic neuron and binds with the receptor inside a ion channel. When that happens, the ion channel opens and allows passage of ions. Okay, so these are the kinds of molecular elements that are present inside a cell membrane, inside a neuronal membrane. Now, that is fine, but how does the membrane itself produce a voltage signal? So for that, let us go back to your high school electrochemistry, right? So for example, you know that if I have a beaker which is separated by membrane, and which has two compartments, left and right. In the left compartment, both compartments have KCl, potassium chloride. But on the left side, the concentration is high, right side, the concentration is low. So if you start with this initial condition, what will happen? Yeah, when you have this kind of gradient in the concentration, what will happen? So if the membrane is permeable to both K plus Cl minus, chloride and potassium, then both ions simply flow from high to low, right? And this keeps on happening, keeps going on until the two concentrations equalize. After that, nothing happens. There's no further flow. It stops there. And at that point, the concentration gradient between left and right will be 0. But something very interesting happens when you use a semi-permeable membrane, as opposed to a membrane which is permeable to both ions. So what happens when you use a semi-permeable membrane? Let us assume that the membrane allows potassium but not chloride. Now, because there is a concentration gradient from left to right, there is more potassium on the left side compared to the right side. So potassiums will start moving from left to right, and because of that, there is a buildup of positive charge on the right side. So that keeps going on. Now, chloride cannot go from left to right, although chloride is high on the left side, cannot go from left to right because this membrane is semi-permeable and it doesn't permit chloride from going from left to right. So now potassium alone keeps going from left to right. So there's an increase of positive charge on the right side. So now if you think about it, initially on the left side, you have increased concentration of both K plus and Cl minus. So both left and right are initially electrically neutral. There's no charge difference. There's no charge on either side, and there's no charge difference between left and right. So what the difference is 0 initially. But because of this selective passage of potassium ions from left to right, there's a buildup of positive charge on the right side compared to the left side. So this right side compartment will start attaining a positive voltage compared to the left side. So if you put a voltmeter, you'll see that there's higher voltage here compared to the left side. So this goes on and on. So the higher voltage here, obviously that voltage will try to drive currents in the right to left direction. Right, so you'll start, there is a tendency, an electrical tendency to push charges from right to left side, right? This is our electrical gradient. But the original flux of potassium from left to right is driven by a chemical gradient because there is higher concentration of chemical K plus on left compared to right. So you will see that very quickly you will start seeing opposing forces acting on potassium. So at some point, both these forces equilibrate, and you won't find any further flow of potassium from left to right. And once you reach this equilibrium point, you will find that there is still a net charge of potassium on the right side, an additional charge. Therefore, the voltage on the left side will be positive with respect to the left side. Okay, so now this kind of potential that is generated when you have two compartments filled with electrolytes and separated by a semi-permeable membrane, the voltage generated is called the Nernst potential. This you must have studied in your high school chemistry, maybe +2 chemistry or something like that. So the voltage difference that you get between two compartments, V1 and V2, is given by this factor times logarithm, natural logarithm, times x2 by x1. So you see that voltage is from V1 to V2. So between 1 and 2 is given by x2 to x1. So if concentration is high in 2, then voltage is higher in 1. Okay, so there's inverse ratio. Now this R factor here is ideal gas constant. T is absolute temperature. ZF, this whole thing is applicable to one ion, right, with respect to a certain semi-permeable membrane. So therefore, ZX indicates the valence of that ion. F is a Faraday's constant. So if you evaluate this quantity RT by ZXF at room temperature, and for Zx equal to 1, right, this quantity evaluates to about 26 millivolts. So that will simplify your calculations. So now if you think of, so you can see how, right, if you have a membrane like this, And if you have, so the semi-permeability of the membrane is offered by or supplied by the semi-permeable ion channels, which are located inside the neural membrane. Because you have potassium ions, which are are selectively permeable to potassium ions, or there are sodium ions, which are ion channels, which are selectively permeable to sodium ions. So like that, the presence of these semi-permeable ion channels are arranging for the conditions required to produce this Nernst potential. So that is how a neuron is able to generate say voltage, a membrane voltage. So now this kind of voltage is generated for every ionic species or ion separately. And the channel itself has some conductance because it's a pore and there is a flow of current from one side to another. So it is obviously offers some resistance to that flow. So electrically, this ion channel is represented by a series between a resistance and a battery. The battery value is given by the Nernst potential. So you call it E Nernst. And the resistance is used in terms of represented in terms of conductance. For reasons I'll explain later. Instead of resistance, we just use conductance as a convention. So now, if you want to represent an ion channel, which is voltage dependent, right? So what that means is the channel can be opened or closed. So it's not a constant channel. So only a voltage dependent channel can be gated by the voltage, so they can vary, right? Whereas their conductance can vary, but if it is not, the other channels which cannot be gated, okay, so then they just remain constant all the time. So to indicate the fact that voltage dependent channels are variable, right? Pictorially, you show that using this notation. You put an arrow cutting across the conductance. It means that conductance is variable. In our case, what it means is it denotes a voltage dependent channel. So you can represent electrically an ion channel as a series of a conductance and a battery. Battery is Nernst potential. Particularly if the channel is a voltage dependent channel, right? You put an arrow across the conductance just to indicate that the conductance is time varying. It can vary. So now if you calculate the Nernst potentials of different ionic species, right? For potassium, the typical figures, like I said, so this K plus O refers to outside, K plus I refers to inside. So like I said, for potassium is high inside and low outside. So if you plug this in, you get a value of EK, the Nernst potential of potassium, to be minus 77 millivolts. And GK, which is this conductance, right, happens to be 36 millisiemens per centimeter square under resting conditions. So now we use per centimeter square because if you think of a patch of neural membrane, right, so you have the lipid bilayer, and so you have all these ion channels with their pore and everything. So all these channels sit across same membrane, and for a given membrane, the outside voltage is 0 volts, and inside is Vm, right? So all these ion channels are in parallel. So when you have a bunch of ion channels in parallel, right, their conductances just add up. So therefore, you can think of some kind of a density of the conductance. That is conductances per unit area. So that's why it is the conductance is given in terms of total conductance in a unit area of the neuron. So we're not talking about single ion channels here. We are talking about conductances of a given patch of membrane, like of unit area, and contents of that kind of channel. So when you say GK, it means the conductance of all the sodium channels, potassium channels, located inside a patch of membrane of area 1 centimeter square. So similarly, if you calculate the Nernst potential of sodium, that and the sodium, like I said, is high outside and low inside. So if you plug this in, you get a Nernst potential of about 50 millivolts. And a typical figure of sodium conductance is 120 millisiemens. These are the values under resting conditions. The neuron is in resting state. So therefore, the sodium equivalent circuit is GNA in series with ENA, and we have seen the values here. And similarly, potassium equivalent circuit are same thing. GK in series with EK. Now there could be many other channels in the neuron which are not voltage dependent. What that means is those conductances are all constant. The corresponding noise potentials are also constant. There could be many of them like that. So I'll think of them as a bunch of different branches. Okay, so these are all like voltage independent channels. So they're all constant. The conductance is not time varying, so they're all constant. So now you know from electrical circuit theory, probably you might have studied it in your first year in electrical engineering course. When you have a bunch of circuit elements like this, you can combine all of them into just one simple series of a conductance and a battery. This is incidentally called the Thevenin equivalent. Okay, so you can combine all of them. So like that, you can construct an equivalent circuit, right? And so this is a reduced representation of all other channels which are not voltage dependent, right? And such channels are called leakage channels, right? Because they're all the time open and they're kind of leaking ions or leaking current into the external space. They're open all the time. Now, there's one more element we need to remember. The membrane itself is also one of the part of the membrane. So the cell membrane has membrane itself and a bunch of ion channels. Membrane itself consists of a lipid bilayer, a double layer of lipid molecules, and there's an insulating sheet. Okay, it doesn't allow passage of ions. If ions have to come, they have to go through the ion channel. They cannot just cut across this membrane. So therefore, since there are two sheets and both are insulating, it kind of looks like a parallel plate capacitor, which again you might have studied in your high school. So you can think of membrane as a capacitor. So if you combine all this, you can come up with an electrical representation of a neural membrane, which looks something like this. The capacitor is the membrane. Then you have one branch corresponding to the voltage sensitive sodium channels. Another branch corresponding to the voltage sensitive potassium channels. Then a third branch, which is actually a sum of all the other ion channels, which are voltage independent. That's right. So this is called the leakage channel, which is just the sum of all the other channels. Now this is a simple electrical equivalent circuit of a neural membrane. And by studying this, you can have some idea of how the voltage is generated, the action potentials are generated in the neuron. So the actual math of it is very complicated, but I'll just use some very simple thumb rules to get an idea of how the membrane potential is generated and how the action potential is generated. I'll just use some very simplistic thumb rules. Now imagine that neuron is in the resting state. That means there's no change in the voltages, no change in currents, right? And when that happens, what is the voltage? So we know that the inside of the cell is called VM, right? And outside is 0, right? 0 millivolts. Now, so the neuron membrane is in the resting condition. What is the voltage? How do you calculate that? So when the membrane is in resting condition, that means no change in voltage, no change in currents. But then when there's no change in the current in the capacitor, since capacitor is C dV by dt is equal to I, voltage is constant, so I is 0. So capacitive current is 0. When that happens, you can just solve this remaining circuit and find that the Vm is a function of other parameters like the conductances and the voltages, noise potentials by this formula. So now if you plug in the resting values of GNA, GK, GL, and ENA, EK, EL in this formula, you get something like minus 70 millivolts, which is the resting potential of a neural membrane. So everything is okay. Now let's consider what happens when right. So this is minus 7, but let us take an approximation to understand what happens in the resting condition. In the resting condition, what happens is a lot of potassium channels are open, and sodium channels are mostly closed. So therefore, if you put this condition that GNA is much less than GK and GL is also much less than GK, you put both these conditions in this formula, what happens is in the numerator you are only left with GK and EK. The denominator you're only left with GK. So you get something like this, which is equal to EK. Right? So the VM is approximately equal to EK when these conditions are satisfied. And so EK is minus 77 millivolts, which is kind of close to minus 70 millivolts. Basically, what we're trying to say is, under resting condition, VM is close to the Nernst potential of potassium, which is EK. Whereas in the excited state, the channel open close situation changes. In the excited state, sodium channels are mostly closed, whereas potassium channels are now open. That means GK is much less than GNA, and GL is much less than also GNA. So if you plug in these two conditions in this formula, you get GNA and ENA survive in the numerator, and GNA alone survives in the denominator. So you get this expression, which is equal to ENA. So in the excited state, when sodium channels open, right, the neuron basically produces a positive voltage. So ENA is 50 millivolts, but actual VM will be about, the highest point is about 30 millivolts. But anyway, this is only a very crude, approximate calculation. So what we understand from this is, you can use sodium potassium channels as some kind of knobs, right, to turn VM up and down. So because what we want to understand is, okay, we understand now why is VM minus 70 millivolts under normal resting conditions. But what we want to next understand is how does it go to a positive value during an action potential. So for that, we understand now that if you to increase the membrane voltage VM, you need to open more sodium channels, because you open more sodium channels, right? The VM goes closer to ENA. ENA acts like an upper limit. If plus 50 is upper limit, but it might go up to plus 30. And if you want to decrease VM, right, open more potassium channels, because if you open more potassium channels, right, VM goes towards EK, which is minus 77 millivolts, and that's kind of like the negative, the lower limit. Okay, so let us stop here. So then, using these ideas, we'll try to explain how an action potential is generated, and we also look at what is neurotransmission in more, in more detail in the next class. Okay.